Crop water requirements refer to the amount of water that is needed to meet the water loss through the evapotranspiration process. These requirements depends on the climate included into the reference evapotranspiration term and on the crop time at its growth stage, represented by the crop coefficient term. Due to the scarcity of water resources, the correct evaluation of water losses by the crop as evapotranspiration is very important in these regions. Therefore, the estimation of irrigation water requirements is directly related to the accuracy in determining crop evapotranspiration. It is especially relevant since accurate estimation could save water and minimize losses, allowing more land to be irrigated and subsequently more food to be produced. There exist several methods for determining crop evapotranspiration on ground. Among the most worldwide used, we find the lysimeters, that are devices that measure directly the evapotranspiration of a crop that is confined within containers. This lysimeter can be classified as drainage or weighting lysimeters. The first one, the drainage lysimeter, calculate the evapotranspiration through water budget, where the excess of water removed by drainage is subtracted from a known water volume applied to the soil surface. The second type of lysimeter, the weighting lysimeters, measure crop evapotranspiration directly through changes in mass. We find also the decovariant technique, which measure both the latent and sensible head fluxes by correlating fast fluctuation of vertical wind speed with the fluctuation in atmospheric water vapor density. This system is normally composed by a three-dimensional sonic anemometer and a gas analyzer, and is complemented by a net radiometer and soil head plates. Another method is the scintillometry. This scintillometry consists of a transmitter and a receiver, which calculate sensible head flux through the scintillation of a transmitted optical or radio wave signal in conjunction with standard meteorological measurement, calculating later the latent head flux as the residual of the energy balance. And finally, I have also included the subflow approach. Subflow sensor measure transpiration flow as the extent of sub within xylem tissue using head as a tracer. Subflow includes two different methods: the steam sector heat balance method, in which a section of the entire steam circumference is electrically heated, and the axial and radial heat loss measured. And the second one is the head pulse method, in which the heater and the temperature sensor probes are placed inside the trunk in a radial direction, calculating sub velocity as a function of the time required by the flowing sap to transport head to a particular location. The suitability of one or another method in terms of convenience, accuracy, or cost for the measurement of crop evapotranspiration depends on the specific characteristic of the study site. However, these on-ground approaches share a series of disadvantages that limit the use. The first one refers to their difficult maintenance. Since a periodic check is usually required as the instruments are located outside and during adverse weather conditions. Another disadvantage is the cost that can reach even tens of thousands of euros, which makes them only large producer or companies can use these ground measurements, not being within reach of small or medium farmers. The installation uncertainties also play a critical role. For instance, edicovariant systems require sensors are installed at a certain height above the plant canopy in relatively flat areas, what is not always possible. Another example of installation uncertainty is found when using the subflow method on vineyards. This crop type has a very complex vascularity that difficult that the sensor installation is representative for the general sub-transport. Additionally, as can be observed in the image, another problem related with subflow is the xylem injuries that are due to the disturbance of conductive tissues surrounding the measurement point. And finally, the spatial representativeness of the measures need to be also taken into account. Generally, these techniques refer to local measures being representative of only a very limited area, which may not be valid for even Ndvi regions. For instance, when analyzing edicovariance or scintillometry data, we need to be really careful about the area this measurement refers to. That is evidenced in the two images, so in this slide, in which we can appreciate that the footprints go outside the study sites. Although I have to say that in both examples, the part outside the study site represent a small proportion of the total footprint contribution. In order to face the previously mentioned limitation, the use of remote sensing technologies has considerably increased in the last decades. These technologies allow for accounting the spatial variability at global, regional, or local scale using drones, aircraft, and satellites. It is also true that even if freely available satellites exist, the cost of performing a flight with a drone or a aircraft are also elevated. Although in this case, the flight cost can be assumed by irrigation association, for instance. Additionally, the use of drones or aircraft provide more flexibility in terms of that we are able to select the moment when the flight is performed as long as the weather condition allow it. The most common approaches for crop evapotranspiration estimation from remotely sensed imagery are the vegetation indexes based models and also the surface energy balance models, differing mainly in the region of the electromagnetic spectrum that are involved in the crop evapotranspiration calculation. Vegetation indices-based approaches are intended on deriving crop evapotranspiration from empirical site-specific relationship between the vegetation index and the crop coefficients. These vegetation indices, among which the most worldwide used are the normalized difference vegetation index and the soil adjusted vegetation index, are calculated using relationship between the visible, more specifically the red band, and the near infrared region of the spectrum. An example of this kind of model is the one that we developed in an ArcGIS environment that is shown in the screen. This model calculates the basal crop coefficient, but using the Ndvi and SAVI, and also this information together with inputs referring to crop characteristics, weather data, soil type, and irrigation system is incorporated into a soil water balance for deriving the evaporation coefficient and ultimately crop evapotranspiration. On the other hand, energy balance models take advantages of the relationship between surface gradients and the energy balance components to derive crop evapotranspiration, and here surface temperature data play an essential role. Most of this model calculate latent head flux and therefore crop evapotranspiration as the residual component of the surface energy balance equation by subtracting the soil and sensible head fluxes from the net radiation at the surface. Within this kind of models, we can distinguish between the one source or two source model, depending if they differentiate between the surface energy transfer of soil and vegetation subsystem or not. Examples of this kind of models are the surface energy balance algorithm for land, mapping evapotranspiration with internalized calibration, surface energy balance system, two source N95, and atmosphere land exchange invert models. However, often these models are too complex for general application due to the difficulties and tedious algorithms that are needed to produce the crop evapotranspiration estimation, requiring, for instance, programming skill. Therefore, there is an advantage for making this model as accessible and user-friendly as possible by programming them in a common software package in order to facilitate and optimize the evapotranspiration estimation by any possible user. And in this sense, I want to show you two examples of two models for crop evapotranspiration estimation. The first one based on vegetation index called ARC dual KC, and the other one that is a well-known model, metric model, that is based on a surface energy balance, and in this case I'm referring to the GIS version, the metric GIS. And in this case, both models have been programmed in Python and incorporating into ArcGIS toolboxes in order to provide this model using a more user-friendly and automated interface. Before moving on to the next section, let me make a brief digression for talking about the use of weather forecast for estimating crop water requirements. In this respect, great advances have been reached in weather data forecasting by numerical weather prediction model for detecting high impact weather processes, regime changes, and global scale anomalies. These advances are a direct consequence of the increase of computer power the spatiotemporal high resolution of the models, and also of the improvement of forecast technologies and tools. Additionally, the accuracy of the weather forecast depends on the model used, the meteorological variable to be predicted, the site topography, the lead time, temporal scale, and the season of the year, among others. In the figure shown in the slide, it can be appreciated an example of the performance of a Cosmo model for predicting different meteorological variables in an Spanish study site. Here, the forecast values shown in the y-axis were compared with the measured one in the x-axis. As evidenced also by other authors, air temperature and solar radiation are the variables with the highest accuracies, whereas the prediction errors concentrated on precipitation and wind speed. Regarding the lead time, taking for instance the solar radiation of the previous example, we observed that the scatter was higher when the prediction was provided with a greater advance. In this case, by comparing the prediction made 3 days in advance with those provided just the day before. Also, in the same study, it was assessed which data source was preferred for reference evapotranspiration calculation. I mean, if we want to irrigate next week, what should we use? The weather data registered the present week, or should we move to the weather forecast for the next week? Well, the answer to this question, at least for this Spanish site and other 3 study sites located in Italy, Norway, and Romania, is shown in this table and this figure. Here, the errors derived from using past weather data were greater than those due to the forecast inaccuracies, with mean absolute errors being halved from 0.62 using the past weather data to 0.30 using the weather forecast. Therefore, the use of agrometeorological forecast data is recommended for reference evapotranspiration estimation, since it allows minor errors if compared to the use of past weather data, and also permit knowing in advance the occurrence of extreme events, as for instance the presence of heat waves. These results open new perspective, advising the implementation of forecast data into remote sensing-based model, and also into decision support tools for irrigation and irrigation scheduling and management, particularly where ground-based weather data are scarce and sparse. The next section focuses on the assessment of groundwater status, which traditionally was performed through the measurement of the on ground of net photosynthesis, stomatal conductance, midday stem water potential, and canopy temperature. However, these approaches result labor and time consuming, since they require from a large number of measurements for being representative to the entire study area. Additionally, the huge variability existing both among trees and inside a single tree difficults the selection of the most appropriate place for carrying out the measurements. For example, the graph in the slide shows a comparison between the canopy temperature obtained from a handheld thermal camera at the sunlit and shaded sides of the tree, respectively, and the near nadir temperature determined from a thermal sensor that was on board an aircraft. Thus, canopy temperature derived from the airborne resulted higher than the canopy temperature measured on the ground in the shaded part of the tree, and lower than that measured in the sunlit part, which is more exposed to the solar radiation. However, when both sunlit and shaded ground measurements were averaged, a one-to-one relationship was obtained with the canopy temperature obtained from the airborne. Therefore, due to the nadir beef angle of the sensor on board the airborne, the remote sensing based approach is able to reveal the spatial within-chrome canopy temperature heterogeneity. Here again, the use of remote sensing technologies appears as a valid alternative for evaluating the crop water status. In this sense, two approaches can be used. The use of vegetation indexes, such as the Ndvi or SHUATS, or the use of thermal indexes, as the canopy to air temperature difference or the crop water stress index. However, here I have to say that Ndvi and SHUATS are structural indexes that are mainly related to canopy vigor, and they should be preferentially employed to detect the long-term effects of water stress on canopy structure rather than the short-term dynamics of water stress. On the contrary, thermal-based indexes are more appropriate. We want to identify fast responses to canopy water status, since leaf temperature increase is the first phenomenon that occurs after the stomatal closure due to water stress. The next example refers to a study in which the suitability of on-ground and remote-based thermal approaches were compared for identifying meal water stress in a peach orchard and its effects on midday steam water potential. This study was performed on 3 peach orchards located in Murcia, Spain, where 870 steam water potential measurements were carried out in 3 years, concentrated in a total of 6 days. Additionally, thermal imagery were obtained on July-August of 2016-2018 using a FLIR thermal camera on board an aircraft. What I want to highlight from this study is that whereas a large number of measurements covering the entire area were needed to assess the crop water status spatial variability, we only needed a single flight per data for assessing this variability. Additionally, it is important to note that also that we needed 3 teams with a total of 15 people for performing such a big number of steam water potential measurement in a reasonable period of time, which represents a very high human personnel expense. When the steam water potentials represented in the y-axis were compared with the crop water stress index values derived from the thermal sensor in the x-axis, a good relationship was found despite showing a wide dispersion typical of the variability of the when working in the field, in the ground. Additionally, in one of these plots, the crop water stress index calculated from ground measurements was compared with that derived from the airborne thermal images. As can be seen in the equation for the computation of crop water stress index from the aircraft, two thresholds were needed. The first one is a lower baseline representing a canopy transpiring at the potential rate, and the second one corresponds with the upper baseline, referring to a canopy where transpiration is completely halted. In this study, these values were obtained from previous studies performed by Bernie et al. In 2012 and Irmak et al. In 2000. On the other hand, the computation of crop water stress index from ground measurements required from a wet reference temperature corresponding with a fully open stomata leaf and a dry reference temperature, determined from a non-transpiring one with completely closed stomata. Such conditions were achieved in its sample tree by spraying a leaf with soapy water and covering another leaf in petroleum jelly on both sides. Results derived from this study evidenced that when comparing airborne and ground acquired crop water stress index as a proxy of water status, the one derived from the airborne was more accurately related to the crop water status defined by the steam water potential. Due to the nadir view angle of the sensor on board the aircraft, the remote sensing-based approach was able to reveal also the spatial within crop canopy temperature heterogeneity. Such intracrop heterogeneity was also partially feasible using handheld thermal cameras, with the main inconvenience of that these sensors are not able to capture in a single image both the shaded and sun exposed parts of the chrome due to its lateral point of view. Another disadvantage of using handheld thermal cameras is that they usually capture a single tree per image, which can hinder the inter-tree canopy temperature comparison. Furthermore, using on-site references, particularly for obtaining the wet reference temperature, is a procedure that is very influenced by experimental errors. These errors derive from the large variation in wet reference temperature within a tree canopy, and also of the leaf wetness level that is very dynamic, particularly under warm and dry conditions. Therefore, this approach is quite dependent on the leaf selection, especially those selected as wet and dry references, and that where the steam water potential measurements were performed. One of the main limitations of the use of thermal data for assessing crop water status refers to the instantaneous nature of thermal sensor. Due to the dynamics of canopy temperature caused by external factors such as instantaneous wind or radiation variability. The quick temporal variability of canopy temperature makes that the instantaneous value acquired by the sensor differs considerably from one moment to another. In this sense, in collaboration with the University of Catania in Italy, we have performed an experiment in which we took 20 zenithal thermal images of the same orange tree at 1 minute intervals. In these videos, it can be observed how the temperature varied in a short period of time. The left side of the image in reddish and white colors represent the sunlit soil between the tree rows, whereas the blue color reflects the tree canopy. Thus, analyzing the histogram, it can be observed that even for this small period of time of 1 minute, the average temperature experienced a variation of almost 1 Kelvin. When we plot the evolution of the canopy and sunlit and shaded soil temperatures, we found that under homogeneous condition, this temperature experienced variation of 2 Kelvin more or less. However, when some intermittent clouds appear in the study site, this range of variation increased considerably, being 7.5 Kelvin for the canopy temperature and reaching values of 15 Kelvin when sunlit soil was considered. These results underscore the fact that despite the multiple advantages of remote sensing, we need to pay special attention when acquiring this type of images. This problem happens even with images taken from drone or aircraft, which are commonly wrongly said to be free of the clouds effect. And the last example that I would like to show you, referring to crop water status assessment, is this small experiment in which we compare the crop water status of a lettuce orchard under 2 different irrigation strategies. In the first treatment, we were in charge of providing the irrigation recommendation based on a model we developed at Sebastopol. I am not going to explain this model in detail, but if anyone is interested, please send me an email and I will provide you the reference of this model. In the second treatment, we leave the farmer to manage the field at his convenience, irrigating in the same way that he usually does. At the end of the season, we perform an airborne campaign with a thermal sensor on board. From the acquired image, we calculated the crop water stress index. And we know that despite if the lettuce we managed presented a slightly better water status with an average value of 0.06, the farmer was able to properly manage irrigation even with water withdrawals, as shown by the crop water stress index value of 0.12. Finally, the last section I would like to deepen in is the use of remote sensing for defining crop management zones. The identification of these management units is particularly relevant for the optimized use of external inputs and for irrigation purposes. We can divide this zoning in function of the environmental compartment on which this zoning is based on. Then we can perform the zoning based on some meteorological parameter, soil characteristics, or plant properties. These zones, at the same time, can be derived from ground measurements, as the case, for instance, of the upper image. So in this slide, where a soil electrical conductivity map was created using the EM38 instrument, this in the image. Generally, when using ground data, it is important to highlight that most time we require from interpolation methods for transforming these point measurements into a map, as for instance, the inverse distance weighting or the configuring method. But here we can also use remote sensing technologies as alternative, which provide directly a spatial representation of the variable we are analyzing. In this presentation, I have included the use of vegetation indexes and thermal data as data sources for performing the zoning. Although other inputs can be also used as the case, for instance, of, for example, of radar satellite data. These zoning maps have multiple applications. For instance, this information can be helpful in precision irrigation strategies and for the optimization of the irrigation system design. In this specific case, the vineyard of interest was flown with a multispectral camera on board, and from this information, the vegetation fraction cover was calculated and later divided in 4 classes depending on its value. In this way, the grower had the ability to irrigate the field according to local water requirement, designing the irrigation lines in a way that they provide more water to the zones of his interest. And the last application that I would like to show you before finishing is how these crop management zones help in the selection of optimum field location for the installation of soil and plant sensors. In this case, the zoning was based on how sensitive were the trees to water stress. For calculating such information, 2 flights were carried out. The first one when trees were well irrigated, and the second one after inducing a water stress consisting in a week without irrigation. By comparing the crop water stress index for both dates, we derived which were the areas more sensitive to water stress within a field. In this case, we indicated in red in the figure in the screen. Based on these areas and on the strategic decision adopted by the grower according to economic and agronomical aspect, sensor might be, for instance, installed in average areas. It is in yellow colors. These areas will provide information of what is the mean crop water status in the field. However, another approach, another alternative could be installing the sensor in those areas that are most sensitive to water stress, which will provide an early warning about water shortage. But at the end, this decision depends on what is the objective that we want to meet. And just for concluding, the main ideas I would like you to take home from this presentation are the following. First, that the accurate estimation of crop evapotranspiration is of paramount importance for facing water scarcity. And here, remote sensing technologies helps to achieve this objective. Second, remote sensing plays an essential role in crop management, monitoring, and in decision-making support. An example of that are the applications that we have described regarding the identification of crop water status and mapping crop management zone. And last but not least, despite its limitations, the role of on-ground measurement is critical, and remote sensing does not have to be considered as an alternative, but as a complement of these approaches. And with this, I have concluded the examples of application that I wanted to share with you in my presentation. But before finishing, let me talk you about a special issue called Water Management in Woody Crop, Challenges and Opportunity of the journal Water, in which I'm the co-guest editor together with Dr. Jose Manuel Mirazábalos. And this special issue is focused on research on irrigation management strategies aiming to save water while maintaining yield and crop quality, especially when employing alternative water sources. Also in studies of other cultural practices that allow for saving water in orchard, as the case, for instance, of mulching. Studies focusing on the effect of climate change or water availability for woody crops, and works using novel techniques for estimating crop water requirements at different application scale through remote sensing technologies. So if any of you are working on some of these topics, we are pleased to invite you to consider sending a contribution for its eventual publication in this special issue. And that's all from my side. Thank you very much for your assistance and for your interest in this webinar. Thank you very much.
Thank you, Dr. Juan. It was a nice presentation on the remote sensing techniques as a tool for agricultural water management. Now, it is my pleasure to introduce our next speaker.
Let's give 5 minutes for question and answer session.
Question session.
Shakti, if you can just, talk about some of the questions that we are receiving.
I have question.
Dr. Juan. Meanwhile, Dr. Tapan Pathak can prepare his presentation.
Yes,
Dr. Juan, it was a really nice session and we enjoyed a lot.
Thank you.
But there are 4 questions which have been asked by different participants. I will go one by one. Okay. The first question is asked by Noor Hassan, and he asked that crop water management model developed in the Python program, in the Python platform, is it available on open domain or we need to develop by our own?
Yes, the first one I showed that that was called Arc Dual KC model is available. So the only thing that people interested in this model need to do is sending me an email, and I will provide the toolbox for being used. And I will send also a user manual for helping in its use. And regarding the second model, the metric GIS model, interested people can send me also an email, but the procedure is a little bit longer, because I have to transmit this request to Dr. Richard Allen, that is the developer of metric, and he will answer me, giving me the permission for sending the model. But I'm sure he's available to send this model. The only thing is that he wants to have a list with the person who we have distribute the model with.
Thank you, Doctor. Our second question is asked by Anuj Trivedi, and he has asked how the canopy temperature is like calculated. Do we model it? He is confused with it, actually.
Okay, here the canopy temperature is, we obtain the thermal information from the camera, and it depends on the specific case, but the important thing is that this thermal data needs to be corrected by the canopy emissivity. I mean, we need to, before to analyzing this data, we needed to make a classification of which part of the photograph of the image was soil, and which part of the photograph was plant, in order to apply different emissivities for each one of the categories.
Okay, thank you, Doctor. Our next question is from Suraj, and he asked that WTI and CWSI, they are the two like water stress indices used to determine crop water stress. Okay, but the results are obtained at qualitative basis. But he asked that, but in precision agriculture, quantifying the amount of water applied should be measured beforehand. So, what to do with it?
Okay, here the main problem that we have when we try to compare on-ground crop water stress index with airborne derived crop water stress index is that we use different equations for calculating both of them. The first, for the calculation of crop water stress index from the airborne, we normalize it using the air temperature, whereas for the ground canopy, ground measure crop water stress index, the references that we used need to be selected on ground. So I think this is the main difference and the main problem that we obtained, and it was the effect that we wanted to evaluate if both methodologies work in the same way or not. And as we observed in our results, we saw that there were important difference.
Okay. Sorry to bother you once again. There's one last question, sir. It is asked by Ashutosh, and he asked that whether the sensors that help in less water applied condition, can we use it? The same sensor can be used in whether the soil moisture is already very high.
Sorry, can you repeat?
will the sensor help in less water application? Can be used in a high moisture conditions?
In a higher moisture condition? Yes, I suppose. I mean, if we are use this, we need to test it because, as we know, when working, the results that we obtain are very conditioned by the arid and semi-arid condition that we have. But I think that this methodology, these methodologies can be translated into other weather conditions, other climates.
Okay. Thank you, sir, for your painstaking efforts. Thank you. That's all for the questions, sir. We can proceed to Dr. Ashish, sir.
Thank you, Dr. Rohan. Thank you, Dr. Shakti. Now, it is my pleasure to introduce our next speaker, Dr. Tapan B. Pathak, a specialist in climate adoption in agriculture from UC Davis, Merced, California. We had the privilege of knowing Dr. Pathak since our graduate school, as he was with Dr. Deepak Lal in Utah State University during his master's, and he was with me at University of Florida during PhD. The title of Dr. Pathak's presentation is Climate Change and California's Irrigated Agriculture, Impact, Adaptation, and Decision Support System. With that, I ask you to give your full attention to Dr. Pathak and help me in welcoming him for his talk. Dr. Pathak.
Hey, first of all, I'm so happy to see familiar faces, Dr. Deepak Lal and Dr. Ashish Ratan Mishra. It feels like you know, the history is in front of me here. And let me share my screen. Okay. Okay, can you see it? Yeah.
Yes, it's visible. So, go ahead.
All right. Okay, perfect. So my name is Tapan Pathak. I'm a cooperative extension specialist with the University of California Division of Ag and Natural Resources, and also with the University of California in Merced. Just to give you a little bit of background about myself, I'm an agricultural engineer and irrigation engineer by training. So my bachelor's was from Gujarat Agricultural University, which is now become a Junagadh Agricultural University in India. And then I moved to Utah State University for my master's program. That's where I met Dr. Deepak Lal, and we were in the same lab working, and then we had a lot of fun stories about that. And so I worked mostly on crop yield estimation using airborne, high resolution airborne imagery. And then right after my master's, I moved to University of Florida, and I switched gears and worked more on deterministic crop simulation models, and using those models to evaluate cotton yield and how different climate patterns are influencing cotton yield in the Southeast. So that was my major activity there. And right after that, I moved to the University of Nebraska-Lincoln as a faculty member in extension, and I worked more in the climate applications in corn and soybean the crops, mainly those two crops. And now I'm with the University of California. So that's my story. Today I'm going to give kind of very high-level overview of climate change and what it means for California agriculture. So before I move into talk about the topic itself, just to give you a very broad overview of University of California's Division of Ag and Natural Resources, you see a map on your left, which is a map of California. And then you see all those red dots, which are UC, which is the University of California Cooperative Extension offices. So those offices have academics and staff housed in those counties, and they do work very closely with people on the ground, understanding their issues and resolving those issues with more science-based and biased information. And so they are the people who are working very closely with stakeholders on the ground. You also see those stars in that map. Those are research and extension centers. So we have roughly about 9 or 10 research and extension centers across California. And those research and extension centers have house both academics as well as cooperative extension specialists who are working on more applied research in both ag and natural resources areas. And then we have those ag experiment stations. So those are tied to 3 University of California campuses. So UC Davis, UC Berkeley, and UC Riverside. They do get a lot of federal funding to conduct more applied agricultural research on bigger issues that's been faced in California and across the United States. You also see a picture on your right, which is a beautiful UC Merced, University of California Merced campus. That's the youngest campus of University of California system. And we have roughly about 8,000 to 9,000 students, both undergrad and graduate students. We have 3 colleges, including College of Engineering, and we have few research institutes, and there are many graduate groups who are very actively working on a lot of interdisciplinary type of research. And although agriculture is not one of the major components of the UC Merced campus itself, because a lot of the ag research has been done at ag experimentation campuses, including UC Davis. But there are a lot of applied research and more interdisciplinary ag research going on, including big data analysis and remote sensing and drone applications, etc. So if there are students who want to pursue higher education degrees in UC Merced, feel free to contact me. Okay, so today I'm going to talk very broadly about climate change, and first part of the talk is mostly going to be what we have observed in the past, and also what we are going to see in the future in terms of trends in temperatures or precipitation, extreme events, including flood, droughts, or heat events, etc., and snowpack, and how those trends are evolving or changing over time. And the second half of my talk is more broadly about how those changes are going to impact, excuse me, how it's going to impact agriculture in various ways. So, either it could be yield decline or chill, which I'm going to talk a little bit about why it matters. Then growing season shift in a lot of those crops, and how climate change is increasing pest and disease pressure, which is ultimately going to impact agriculture. Then I'm also going to talk about a few efforts that I started in California regarding decision support system, and how effectively we can use climate and weather information and put them in a decision support perspectives. And so it's not just 1 or 2 parameters, but it's rather more complex system, and how can we tailor that information for different crops in California. and there are some research directions, although that's not a very comprehensive list. These are some of the things that, you know, the research, we need a little bit more research on, and this is all specific to climate change research in agriculture. So you might have heard a few facts about California agriculture yesterday from Dr. Daniele Zacarias' presentation. But I just wanted to reiterate some of those points and just to make a point that, you know, why it is important to know what's happening to California agriculture, because it sort of leads many crops and commodities in United States, and also has a lot of exports, especially the nut crops to India, Asia, India, China, and parts of Europe. And so I'm going to briefly mention about that. So California has a Mediterranean climate, which means that most of the rainfall that we get is during the winter time, and during summer it's almost no rainfall and a full solar radiation and clear skies. And so, you know, that provides very optimum growing conditions for a lot of crops, especially if they're irrigated. So we have 76,000 farms, and there are more than 400 commodities that are grown in California in different parts. California also has a lot of microclimate in different zones, and so that provides unique crop growing conditions in those microclimates. So in terms of the land, roughly 100 million acres of land, 43 million is used for agriculture, so roughly about 40%. 16 million acre is a grazing land, 27 million is a cropland, but only 9 million acres where most of the production agriculture happens is irrigated land. So irrigation is very concentrated effort in California, and then that's why you see a lot of water and irrigation related research going on in California. California leads the nation in dairy production. 2/3 of the fruits and nuts are produced in California, 1/3 of the US vegetable production. In terms of the farm gate value, which is total value of the crop leaving the farm, is roughly about $45 to $50 billion, which is a huge industry. And if you compare, the top, which is California top rank, and the second rank is Iowa, is roughly about 27 million. So look at this difference in the scale of production in California compared to other states in the United States. If we look at top 10 most valued commodities in California, dairy being on top with more than $6 billion. Grapes is second with $6.25 billion, followed by almond, cattle cows, pistachios, strawberries, lettuce, floriculture, tomatoes, and oranges. So some of those commodities do vary year to year, depending on their values. But roughly, these are the sort of top 10 most valued commodities in California. So let's get to the little bit of the basics. I want to distinguish, climate variability and climate change. We talk about both climate variability and climate change quite a lot in applied climate science. So when you talk about climate variability, it's a measure of short-term fluctuation in climate. And in average climate, which is above or below their average value, and so in climate science, this average is roughly defined as a 30 years average, right? And so that fluctuation is still a very short-term fluctuations. You see two examples of this oscillations, which has both orange and blue colors. Both of those indices are oceanic temperature oscillations, the sea surface temperature oscillations in equatorial Pacific region. So, for example, this multivariate ENSO index is one of many indices that define El Nino, La Nina, so the El Nino Southern Oscillation patterns or the phenomena, right? That variation is a short term, which can fluctuate from 6 months to about 2 years. And their fluctuation is rather short term. But that fluctuation defines those phenomena. There's another another oscillation, which is a little bit of longer term on a decadal scale, which is called Pacific decadal oscillations. So these are, you know, two examples of large scale atmospheric and oceanic circulations that do influence climate quite a bit across the globe, and that is, you know, still defined under the natural variability phase. But when you talk about climate change, it's a longer term continuous change, and so, you know, either it could be increasing trend or decreasing trend depending on which variable we are studying, and it has to be statistically significant trend. And so we'll talk a little bit more about some of those trends. So this is an example of how this natural variability can influence climate across the globe. The top figure shows temperature, the climate variations in different parts of the world during December through February. So if you see United States here on your right side of the map, during El Nino years, or during especially the winter time, you can expect that the southern part of the United States expect cooler and wetter conditions, whereas the northwestern edge of the United States and Canada is in a warmer temperature regime. You also see India here, and during El Nino and during the December through February time frame, or, you know, the winter time frame, winter is expected to be warm. But more importantly, if you focus on June through August, which is kind of the monsoon season in India, and as you can see here, you can expect drier conditions during an El Nino years. So this is still an estimation or an expectation because of those large scale variations. But this is just an example that, you know, how that can influence climate, and that is still under the natural variability part. So let's talk about the global change that we have experienced in the past. This is a 5 years moving average simulation that was compiled by NASA that looks at temperature anomalies, which is you know, deviation in the temperature from their average values. All those blue colors show that, you know, the temperature during early years, which is that you can see on the top right corner, is cooler than normal. But as the years progresses, and every single year since 1970 onwards, on an average globally, has been warmer than normal. And in the recent years, there are a lot of years has broken those records, being you know, the warmest years on record and things like that. And this is the latest one is 2013 to 2017 average, and as you can see, almost the entire globe has experienced warmer than normal temperature ranges. And you know, that's a gradual change, right? But you know, then we also have those variability from month to month, from day to day, right? This is one example. This is the top figure is March of 2018, and on an average, you can see the March of 2018 was roughly the average March for United States. But on the other side, Asia, on an average, has experienced much warmer than normal average, and some areas have record warmest years. The record warmest March for the entire record. 2 months later, the second figure is May of 2018, and if you see United States, on an average was the warmest May on record for the whole U.S. And so there's a lot of variation as well, but it also depends on when those variations are hitting agriculture and having those impacts. So this is again historical data looking at years 1895 to 2017. And again, this is California. And if you focus on the central parts, E and G, which are Sacramento Delta region and San Joaquin Valley, which combining together, it's called Central Valley. That's where most of the agricultural production happens. And for California, and including most valued nut crops in almond, walnut, and pistachio. And as you can see, the rate of increase in the minimum temperatures is substantially higher than the maximum temperatures. And that trend is consistent in all those different zones. The most minimum temperature that California has experienced is in the South Coast, where a lot of small fruits and vegetable production happens, and followed by the Central Valley. And many of those areas, maximum temperature increase is not even statistically significant, but minimum temperature increases has a lot of negative consequences on agriculture that I'll talk about in the later slides. Another important point to mention here, this region D, which is a Sierras region, that is where most of the snowfall occurs in California, which is a natural water storage for California. And in the recent years, that area has experienced quite high increase in the minimum temperatures, and that results in earlier snow melt and less snow, more water, and less overall runoff. And so that kind of complicates it even further. This is just the same information in a different perspective. So if you look at this vertical line, which is the baseline average temperature from 1949 to 2005, and this orange is deviation from that average temperatures in terms of the maximum temperatures, and the green is deviation in the minimum temperatures. And as you can see, that deviation from that average in the minimum temperature is roughly between 2 to 4 degrees Fahrenheit, whereas the maximum temperature is between 0 to 2. And so there is a clear difference, or the trend, where minimum temperatures are increasing at much higher rate than the maximum temperatures. Okay, so in terms of precipitation, there are 3 location time series that I'm putting here, 2 in the northern part of the state and 1 San Diego in the southern part of the California. And as you can see, none of those time series show any type of trend in precipitation. So there is not a lot of confidence in models to show that whether there is a increasing or decreasing trends in precipitation, but there is more confidence in from the model projections perspective, is that overall wet season for California is shrinking, and so even if we get rain, that rainfall is going to come in a small, the smaller frequency, but then more intensity. And so you might get more intense events rather than having those gradual precipitation events occurring. And so other way of saying with this variability is that this state in general and southwest western US in general is going to be vulnerable to both flood and drought conditions in California, in this region. Okay, so this is a US average, and what it shows is that in a recent years, extreme single-day precipitation event has been occurring quite a bit. And so 7 or 8 out of top 10 extreme single-day precipitation event in general for United States has been occurring since 2000. So in the recent years, you're kind of seeing this upward trend. So if we put temperature and precipitation data into these 4 categories: dry hot, dry cold, and wet cold, most of the recent years are either in the dry hot category or wet hot category. And more specifically, if you focus recent 15 years, 9 out of those 15 years fall under dry and hot category, which means that state has experienced a lot of drought conditions in those years, and so in 2000, starting from 2012, California had exceptional drought that lasted until 2017 or so, and so many of those years are part of that dry hot category here in this figure. So apart from that, another important indicator is extreme heat days. So the way this is defined is the extreme heat days are 99th percentile of the time frame that you're looking at, and this is just an example of a place where I am at, Merced. And what it shows is that in historical years, so from 1960 to 1990, there are roughly about 4 days where temperature exceeded 104 degrees threshold for this region. As opposed to that, in the future, under a low emission scenario, so which is a RCP 4.5, which sort of tells us that if we are very aggressive with our mitigation or greenhouse gas mitigation planning, then that's the pathway we are taking. So even under that optimistic scenario, we are going to get 40 days when temperature exceeding 104 degrees by 2070 to 2099. So that's a significant change from current conditions, and there are a lot of negative consequences of extreme heat events and how it is impacting agriculture. So in addition to having more days with temperature exceeding that value, we are also seeing a distribution. So in a historical years, most of those extreme heat days were populated from June through August or September. If you move into the future, those June through September is denser in terms of getting more days, but those extreme heat events start as early as May and last as long as October. And so if you think about agricultural productivity, but on the other side, a lot of specialty crops that are grown in California are labor intensive, and so the farm workers health impacts are another big consequences of these extreme events. You might have seen or heard a lot about, wildfires and how dangerous those wildfires occurring in California. And so under future climate, those wildfires are going to increase quite substantially. Even, in today's season, those wildfires start very early, last longer, and they're intense than it were in the past. So the first figure here shows the wildfire frequency, and it shows that, how well it is correlated with the springtime temperature increases, spring and summer both. And in the recent years, that is gradually going up, and at the same time, it is impacting wildfires too. It is also correlated well with the timing of snowmelt. Remember, I mentioned about, minimum temperature increases in the Sierras, and that is impacting snowmelt, and that is also impacting wildfires. The reason I'm showing this, wildfire consequences here is because there is also an indirect consequences of wildfire on agriculture land as well. And so a lot of those, denser forestry areas also has a lot of specialty crop production, such as, table grapes, wine grapes, and other important crops, including vegetable and small fruits. And they have indirect impacts, such as, damages through due to wildfires, but also, power outages and not having resources to irrigate those fields because of the damage and things like that. And so there is a indirect consequences of wildfire on agriculture. We talk about drought a lot, and so drought is not a new phenomenon in California. It's always been there, but in the recent years, those droughts are becoming more and more frequent and more intense. And so this is one of the famous indicators of drought that's been used. It's called Palmer Drought Severity Index, which is kind of the, in an easier term, it's relative dryness is what it's measuring. Although it's not a good representation of agricultural drought in California, but it's just as an indicator that, we are experiencing that extreme or exceptional drought in recent years. So I mentioned about snowpack in the Sierras region. That's where most of the snowpack happens and stays there during the springtime, and that becomes a natural water storage for California. Historical ranges is between 1960 to 1990, and under low and high emission scenarios, we are going to expect 48 to 65% loss in that snowpack in that region. And so that's going to be a substantial loss, and ultimately it's going to also impact agricultural water supply. Okay, so we talked about very briefly though about those trends in the different variables, including temperature, precipitation, droughts, and extremes. And now the second part, let's talk about what are the consequences on agriculture. So if we think in a global perspective, and if you think in a food security format, according to FAO definition of food, moderate food insecurity, which means that insufficient money or resources for healthy diet, or lack of food in once in a while, things like that. But in a severe food insecurity component, person is called severe food insecure when it runs out of food or gone the entire day without eating at times during the year. So none of the region or individual should be in that category. But unfortunately, in recent years, we are kind of seeing this gradual increasing trend. So if you look at Africa in last 3-4 years, so 2014 to 2017, severe food insecurity has gone up to 7 to 8%. On a global scale, roughly about 2%, and it's gradually crawling up in Latin America, and you know, there are many other places too. Asia, there's fluctuating overall, but you know, that is a concerning fact, and given that we are you know, the global population is increasing, and rate at which the production is happening, there is not a real match with matching with the global population food needs, and so that's a big issue in agricultural production. So if you think about, you know, the main staple crops, rice, wheat, and rice, wheat, and maize, and so if we think about those three, majority of the calories, so roughly about 50 to 60% of the calorie consumed by the global population or the regional population comes from those main staple crops, and of course different regions may have different you know, combinations of calories, but those are the main crops. And you know, there was a paper by Lobel in 2008 where they looked at, you know, how 1 degree centigrade increase in temperatures is going to have an impact on rice, wheat, and maize production. And as you can see, there are many parts of India where it shows that, you know, there are different types of models. So, you know, in this table is comparing some of those very highly used deterministic models such as series and SOIGRO and other mechanistic models, but then also they're comparing with some of the statistical models too. And in general, what it's showing that, you know, the yield decline is anywhere from, you know, 2 to 10 to even 17 to 18%, depending on the region, depending on the model that we are. Again, this is the model-based study, so of course there could be a lot of uncertainty, but the important thing to see is that with 1 degree increase in temperature can have a significant impact on agricultural production or yield. When we think about crop sensitivity to different climatic parameters, when we think about vegetables, they are more sensitive to optimum, you know, their extreme temperature changes, and there is a lot of vegetable production in California, which already seeing some of those impacts. Perennial specialty crops, there is a yield decline due to chill requirements. So, you know, some of those specialty crops or orchards in California, and you know, I mean, as a crop itself, they do require a certain amount of hours when temperature below certain range, below you know, 32 degrees Fahrenheit or below 30 degrees Fahrenheit. and then once they accumulate certain chill, their physiological process tells them that, you know, now it's time to break the dormancy and start the bud break and the blooming process. So when they don't get enough chill, that impacts their blooming, and ultimately that impacts or disrupts their production. And so there is a huge issue with perennial specialty crops with respect to the chill requirements. When we think about soybean and alfalfa, elevated CO2 is associated with reduced nitrogen protein content. Corn, rice, and cotton, you know, the temperature increase is a key stressor for those crops. So 2 years ago, Dr. Danieli Zakaria, myself, and many other colleagues looked at a lot of studies done in California and published a peer-reviewed paper on, you know, climate change trends and what sort of impacts that agriculture and California is experiencing. And it got a lot of attention, and it's one of the most accessed paper for this journal. And so this is an open access paper. If you want to learn more about California agriculture and how climate change is impacting, this would be a good paper to read. And this is an open access. So I have this link on this slide that you can use and look at the paper. If we think about California, so one thing I want to mention about California, we have a lot of those specialty crops, but unfortunately, most of the crops do not have the mathematical crop simulation models or robust models that can be used and applied for a lot of studies, including irrigation, water, and yield trade-off type of studies as well. And there are very few models. So these are some of the examples of crops that there was a model run to assess impacts of climate change on those crops with different emission scenarios. As you can see, alfalfa, which is one of the major crops in California, see almost no yield decline with respect to climate change, because there is no reproductive phase in that crop. And as opposed to that, sunflower and cotton and wheat and rice do see yield decline anywhere from 9% to 29%. Again, I want to mention that in this study, they did not look at water stress, which could be a major factor, and that could change those numbers quite a bit. And they did not look at any adaptation measures too. So this is kind of as a reference that you might experience that yield decline quite significantly in some of those crops. So I mentioned about that chill accumulations. This is California on a horizontal scale. So it's kind of vertical California on the Central Valley on the horizontal scale, and what it shows is that in 1950, for example, you are getting chill hours anywhere from 10,000 to 1,200. Under future, I mean, even by 2000, there is a 30% reduction in total chill that California has received. And in the future climate, it's going to decline even further, and it's going to have a major impact on that production. Length of the growing season is another indicator of climate change. So it's a time from last spring freeze to first fall freeze. And so the entire time frame is increasing in general for United States, but more specifically in California, it has increased almost by 3 weeks. But on the other hand, so we published this study a couple of years ago, where we looked at processing tomatoes and how temperature increases can have an impact on their phenology. So, the time from emergence to maturity for processing tomatoes in the historical years versus the future years, what we found is that under future climate, that total time frame from emergence to maturity might shrink almost by a month. So we did not look at the potential yield decline, but if your total time from emergence or the total growing season time, if it is shrinking significantly, it can have an impact on yield as well. So I would say one positive about climate change on agriculture is a lot of regions in California were frost-prone regions. So citrus, for example, or avocados, those type of crops are really frost sensitive. But with the climate change and temperature increases, we are seeing less and less frost exposure in many parts of California. And so, that can have significant expansion on those type of crops to the regions that were frost prone. I mentioned about impacts on weed and pest and diseases. So one of the major pests for nut crops in California is navel orange worm. And you see two slides where one shows only 2 counties in a red color, which shows that, you know, in the historical years, there are only 2 counties that might have experienced, you know, the pest infestation to the 5th or 6th generation, but into the future, the entire area might experience, you know, pest infestation and have significant damage to the crop. Another impact is of course on weed infestations as well, and since we are not getting enough frost, then it can also have some more added pressure to the agricultural production. So we talked about you know, the impacts and trends. I also wanted to briefly mention about, you know, one of the potential adaptation to those climate and weather related risks would be how effectively we can use climate and weather information and put them in a strategic agricultural decision making processes. So when you think about you know, United States or any other country, really there is no shortage of data. For example, we have a lot of places where you can get historical data. There are a lot of places where you can get, you know, even the daily scale, downscaled climate projections data. You also have this climate forecast for, you know, next 8 to 14 days, or even a seasonal forecast. You also have those large scale teleconnection patterns. So, you know, in terms of that kind of data, raw data is, you know, there is no limit to that. So there is already enough data out there. The big challenge is how can we use that data into more of a decision-making process. So, you know, US Department of Agriculture reported in one of their publications that, you know, they are facing this challenge of translating that data into more of readily understandable information. That's the same priority for California through California Department of Food and Agriculture. So they want to compile list of growers' need of weather-related information and products. And then we heard from, you know, the yesterday's speaker. So there are a lot of those information and services are out there in India too, which was pretty impressive. The National Climate Assessment also mentioned that, you know, we need this decision support system, but it also needs to integrate, you know, values and goals of stakeholders and their perception of risk and things like that to make it more useful to the community. So I mentored a PhD student from UC Berkeley. Now she's a postdoc, Kripa Jagannathan, and there was a big team of people where Kripa mainly interviewed a lot of almond growers in the valley to understand, you know, what sort of role of climate and weather information in their decision-making processes, what type of data they want, and what sort of formats they prefer, and how can we disseminate that kind of information. So that was a very interesting project, and then we learned a lot. And, you know, one or two things I want to mention that what we learned is from growers' perspective, climate is always a hidden driver. So it's not a major factor for them to make those short or long-term decisions. For them, economics or logistics of operations, such as, you know, a planning process or when to harvest, when to plant, things like that. Labor availability is a big issue. Tradition, history, experience, those are main drivers. And a lot of times climate is sort of working as a hidden driver. So I think from being a applied climate scientist, I think our job, or being a scientist, our job is to find ways to integrate that risk perception in all those sectors, and not just worry about or not just focus on the production. And they also mentioned that, they really need crop specific indicators. So, 1 or 2 degrees change might not matter much on crop A, but it matters a lot on crop B. And so, how can you provide crop specific indicators for, if you talk about almonds here, chill hours during winter time, frost patterns, wind, temperature, rain, etc. during bloom, temperature, extreme hot days during maturity, and rain, the risk of rain during harvest, or extreme hot days during harvest. So those kind of indicators are much more resonating with growers. So we recently launched a decision support system project through funding from US Department of Agriculture and through working in collaboration with the USDA climate hubs. We are trying to integrate both historical weather data and future weather, the historical weather data, short-term weather forecast, and climate projections all together to provide, heat advisory, frost advisory, crop specific phenology, and crop specific pest and disease advisory, and other indicators. And so, and then we try to make it more crop specific. But more importantly, we don't want to make it in silo and then just, give this information that here, okay, we have this product for you to use. We really want to engage, this ag community and try to work with them and provide that information that is more customized to their needs. So, just to give you an example, if the frost is or freeze event is going to happen, the user can click anywhere in the map in California, and the map can provide, this is, it's a beta version that we are trying to still fine tune it, but it can provide that, frost risk and how many days in the future, in next 7 days or next 10 days, you are going to have temperature below, below freezing or below 28 degrees Fahrenheit or things like that. And so, and then also providing, if they select on a crop, then also provides, what sort of frost protection that you can do for your crop in order to alleviate some of those risks. Although you cannot cancel all the risk, but at least you can try to minimize that. In a similar way, we are also working to provide heat advisory system. This is actually a map from today, and as you can see, a lot of places in California is red, and what is telling is that there is a big heat event occurring in many parts of California, and it's going to have some impact on production. And so, you can the growers can get this advisory 10 days ahead of a time, of course with some uncertainty because it's a forecast, but then they can be prepared to take actions on that. I also have another project on strawberry yield forecasting. I just wanted to briefly mention here that we installed a lot of sensors, meteorology sensors, the leaf canopy temperatures, ambient temperatures, and some of those variables that we did not put in the field, but then we collected from the nearest weather station and try to integrate all those variables in a machine learning model. So we compared both neural network and random forest for strawberry forecast. So the motivation here of creating the strawberry yield forecast had two motives. One is, of course, to get more accurate yield predictions or yield forecasts for next, next 10 days or next week. But then another motive was growers need this forecast to know when they're going to have this peak yield or the peak production in strawberries. Based on that, they can effectively manage their labor. because labor is a big issue in California, and strawberry needs a lot of manual farm worker power, and so we are trying to fine tune this with more variables in the future and try to validate it further. There are, I mentioned about CalAgro climate effort. There are other parts of US, they also have this kind of very successful model. Agroclimate is an example from University of Florida. So my PhD co-advisor is a founder of this program, and there are a lot of growers are daily or periodically using their products on their website. There's another one on specific to corn in the Midwest, where a lot of corn production happens, and so we are trying to adopt some of those technologies and some of those products and use it for California, but make our own products as well. So this is my last slide. There are, as I mentioned, there are a lot of potential research needs, but when I think from climate change perspective and when I think about agriculture, I think we still have a long way to go in order to understand and quantify impacts of exposure to those extreme conditions, and because different crops do respond to those extremes differently, and we need to do a lot of effort. We need to make a lot of effort to quantify and make a good inventory so that we can work towards the adaptation side. Research, in terms of the research, if we really want to make an impact, it has to be locally relevant, and then we need to be more holistic, involving scientific, social, and economic factors, because a lot of times that economic factors are the drivers, right? There are a lot of studies are based on models, but ground truthing is really important, and we need to get those models ready for creating those impact studies, and then also for crop performance under limited water conditions and things like that, which are key research areas in California. Of course, working more towards improving forecasting skills. But the last point is super important, is simply providing this information, scientific facts, is not sufficient. Technology and solutions need to integrate end users' challenges or their perspectives to make it more and help them translate science into meaningful actions. So here is my contact information, my email and office phone number. So if you want to know more about any of my work, or if you have any collaborative opportunities, feel free to email me. Thank you so much.
Thank you, Dr. Pathak. It was a very nice presentation. We learned a lot of things about California. We knew about Florida earlier. So I am switching to Dr. Shakti. She may put the questions which is asked by audience and participants. Dr. Shakti.
Thank you, Ashish sir. I have few questions, and they are simple general questions. So Tapan sir, Ashima asked that can we correlate this California's finding with India? Can we correlate your findings of California with India?
Okay, so as I mentioned, I think those are two different approaches. So if you think about models that we use, if those models are more physically based or mathematical models, technically you can calibrate those models and apply to in different regions. But as I mentioned, having those specialty crops in California, a lot of those crops has statistical models, And one of the limitations of statistical models is that you need to it can work great in a region, but you have to try and see whether it validates in other regions too. So answer is both yes and no, depending on which models we are talking about.
Okay, thank you, sir. Stuti has asked that apart from adaptation, other the general adaptation which we are like moving about, what are the simple measures that can be taken to reduce temperature or maybe the greenhouse gases? What is the simple step, the general step that can be taken?
I could not get the second part or your voice. Can you repeat the question, please? Sorry.
Apart from adaptation, what are the simple measures, the general measures that a person can take to reduce the amount of greenhouse gases or maybe in order to reduce temperature?
Okay. And then are you referring to agricultural production or in general?
Yes, sir. Agriculture production and overall sustainability of country.
Okay. So I think, if we think about agriculture and the greenhouse gas emissions from a lot of practices, many of them do come from fertilizer applications and pesticide applications. So, if there are ways in which we can make fertilizer application more efficient and based on the recommendations from the scientists who are working on those different crops, and if we can reduce that, there is going to be much more reduction in greenhouse gas through that kind of practices. And then same goes with livestock and others. And so I think in general, those kind of best management practices, they also work on reducing greenhouse gas emissions as well. So that's one example. Another example would be, moving more towards renewable energy. And it's one way or the other, if you can enhance or increase the use of renewable energy, that would have a substantial impact on greenhouse gas emission reduction. So, India has a pretty amazing or impressive project on a solar implementation on canals or aqueducts. And so that has a co-benefit, right? So it improves, or it creates energy source, but it also reduces the water evaporation from the open source. And so, that kind of approaches are examples of that.
Okay. Thank you, sir. There's one last question. In one slide, you have said that if we reduce the frost, so it will be viable for in a shorter period. Does it is viable for a longer duration when we talk about century, or if
Sure.
there will be less frost throughout the century? So it will be, I guess, it will be negatively affected. So what are your views about that?
Well, I mean, so frost is frost itself negatively impacts citrus, and so those are specific examples of crops. If we are going to get less and less frost into future because of temperature increases, it reduces the frost exposure. And so that allows some of those regions in California to increase that production of those particular crops in that region. And so that is only advantage to that particular crop or selection of crops. But maybe as a consequence, it reduces also the chill hours or the chill requirement for nut crops. And so it really depends on which crop we are talking about.
Thank you, sir. There's one last question. It just came. So can we take it?
Yes, please go ahead.
Yes, sir. Is there any measure to mitigate the high temperature effect on vegetable crops?
Yeah, I mean, so there are many practices are happening, such as adding a shading or creating that high tunnel and that kind of thing. So that sort of buffers the temperature ranges. But many times those practices do come with added financial burden, and then so that ultimately impacts on the consumers use of those principles. So yeah, I mean there are some adaptation measures out there, but it just it has those trade-offs too.
Thank you, sir. Thank you for your patience. Thank you.
So,
All right, thank you.
thank you, Dr. Pathak. I have one more question. What challenges you are facing in terms of climate changes when you compare the climate from Florida and climate of California?
Well, Florida climate is I still miss that climate. I think the challenges are one of the bigger challenge for, I mean, if you think about agriculture is water. There is always a shortage of water in California, and there is also the competition between urban and agriculture use of water. Given that this area is experiencing a lot of droughts, and when you compare it to Florida, where there is no comparison between amount of rain you get in Florida versus you get in California. So that's one of the bigger differences I can see.
So what are the challenges in next decades in terms of climate change respective to USA and India?
So I think one of the bigger challenges that pretty much entire globe is experiencing with respect to temperature is extreme extreme heat events, because those extreme heat events can impact production and almost damage the entire production quite a bit. So that is a lot of places are already experiencing that. And also another big issue is related to increased pressure on pests and diseases, because with this temperature, and especially the minimum temperature increases, that increases the new pests and diseases are happening to these regions where there is not enough information available. And so how to tackle those, and those kind of things are ongoing challenges. And of course, on top of all those challenges is challenges related to agricultural uncertainty related to agricultural water. And so those, to me, I think are the bigger challenges overall in the global scale.
Thank you. Thanks a lot, Dr. Pathak.
Thank you so much. I really enjoyed talking and interacting with old friends.
No,
Same here. Same here. We love it.
It's a hard time for you. Thanks a lot. So, our next speaker, now please welcome our head of Geospatial Technologies, Center for Geospatial Technologies, Dr. Deepak Lal. Dr. Lal did his master's from Utah State University in Department of Biological and Irrigation Engineering in 2006. He worked as a remote sensing specialist at David's Engineering in California, USA for 7 years prior to joining SHUATS in 2013. He is working as a head of Center for Geospatial Technologies since its establishment from 2016. So with that, please welcome Dr. Lal.
Thank you, Dr. Ashish. Let me share my screen. Can you all see it in a full screen mode?
Yeah.
Okay. In today's presentation, what I have done is, the title says that geospatial technology for sustainable and profitable agriculture. So far, what we have heard about from our different speakers, how to manage agriculture, how to do irrigation management, and various aspects of crop management via remote sensing and GIS. I have made this presentation much more simplified, as well as just an overview. So we have already seen details of these techniques from our expert and guest speakers. From my side, I would just like to show you an overview and some of the work that I have done, particularly for Allahabad Prayagraj district. And I prepared this presentation in a lighter mode, and just to be more informative, and also it also targets the prospective students or people who are interested. Maybe they can join remote sensing and GIS, and they can consider their future in remote sensing and GIS for managing agriculture. So here we go. I mean, before joining SHUATS in 2013, I was in US. I was working with David's Engineering as a remote sensing specialist. I worked there for about 7 years. And prior to joining David's Engineering, I was studying in Utah State University. I had batchmates at Tapan and Daniele. We were all there in the same lab, in the remote sensing services lab. Even Dr. Harikeshan Jayanti, he was our senior, so he was also there. So it's the same team, and we have worked a lot using remote sensing and GIS in that lab. And in those times, I'm talking about when I started working in 2002, we didn't have drones. So we used to fly in this small Piper Seneca plane, a 6-seater plane. It had multispectral and multispectral cameras and thermal scanner. So we used to collect imagery on our own, and we used to process it, and we used to use it to give information, to provide information for the growers and the farmers there. So anyhow, let's move forward with my presentation. So the content is simple. We'll just talk about geospatial technologies, what they are, why we call them geospatial technology, what does it include, and then where these technologies can help us in agriculture, like health monitoring, irrigation management, yield prediction, and water use efficiency. So first of all, let's see some challenges. I mean, these are existing challenges, and in this particular situation in COVID era, things have got more complicated. The most important thing is farm monitoring, our agricultural field monitoring. In India, normally, we believe a lot of in, going to the field, seeing the field through our eyes, and just checking at regular basis whenever it's possible. We have workforce, but in this situation, there is a huge imbalance in workforce. There are places where, people have migrated from those places, and most of them are farm laborers, farm workers. So it's a huge imbalance. And then where we have people, still we have to maintain social distancing and things like that. I mean, this sort of limitations will be there. And then we also have limited input resources. There are challenges in countries, developing countries, to have as many resources as we can. So we need to be very particular about what resources we have and how we can use to the maximum. And then of course logistics limitations, the planning part, when there is production, how to store it, where to store it, what should be the market price, and so many things related to planning. So what do we need here? First of all, we need to produce more with the optimal use of resources. So I mean, there is an average production, and then there is a potential production. So we need to reach that potential. And then obviously for that we need more information for better planning. So let's see what geospatial technologies means in very simple and basic terms. So it comprises of 3 things. 2 you can see on the screen: geographic information. What does it give in terms of agriculture? You can see here a satellite image, and we can see fields, but we need the field boundaries to extract information. So through GIS, we can prepare field boundaries. And then remote sensing, it gives us data like satellite images, where we can apply science and we can, manipulate the imagery and get some information, run models. And the third component of geospatial technology is GPS, Global Positioning System. So it gives us the specific information of the particular thing that we are looking at, be it field or any structure. So for example, this is our a top view or a satellite view of our university. We wouldn't know until unless we have gone there, taken our GPS readings and put back those GPS reading on this satellite images, that what we are looking at it is. So for example, we are looking at, we have on the left side, we have basketball court, we have athletic field, we have different buildings. So we need locations. So when we combine GIS, remote sensing data and locations, then we can extract information, we can do science and extract information. So let's see. These are some of the examples of my work done for Prayagraj district. And it's about agricultural management. Let's go ahead. So if it's about Allahabad, or the new name is Prayagraj, so don't get confused. Let's see some background information about this Prayagraj region. It's primarily an agricultural region. The population is around 59 lakhs and 54,000. So in terms of million, it's almost 6 million. Then the area is 5,400 square kilometers. It has 8 blocks, so it has subdivisions, which are called blocks. The cropping pattern, as we can see, it's a primarily agricultural area. So almost 80% of the total Allahabad area is irrigated, grossly irrigated. And then we have 3 cropping seasons: Kharif, Rabi, Zaid. Rabi is the winter season that I'm going to show you examples from it. And the major crop in Rabi is it's wheat. So I'm going to show you wheat example. So let's see some basic fundamental statistics of wheat. So UP is among the largest, I could say top 2 or top 3 in the country, wheat producing states. And major part of that wheat is also produced in Allahabad and surrounding districts. So this particular region is very important in wheat growing. And as we can see in the chart, the district average for 2000 to 2014 was 2.2 tons per hectare. And we are below from the country average. These are all data available on the government side, 2.2, 2.8. And the FAO, you might have heard the name, Food and Agriculture Organization, they releases these standard documents or guidelines and their recommendations. So according to this FAO guideline number 33, there's a bulletin or booklet. They say that in typical in these areas in our country, especially in semi-arid regions, the potential yield for wheat should be 4 tons per hectare. So, it's apparent that we are producing lower than its potential. So again, let's see. The first aspect of agriculture that I would like to focus on is crop health monitoring. When I was working here, we have an extension department and also an agricultural science center, which is called KVK in Hindi, Krishi Vigyan Kendra. What we observed is that, we are underproducing for, obviously for several reasons, but one of the most important reason is the proper monitoring of crops are not being done on time. Like, farmers, they go to the field, they will check their fields, but they wouldn't realize that the stress is coming onto that crop, because from naked eye, the field might look green. But if you use a remote sensing data or a near infrared image, there could be stresses. So in the remote sensing image, as you see, there are areas which are green, which looks fine. But then there are areas which looks yellow and red. Those areas could be problem, and we have to check them in time, on time. Otherwise, they might spread as well in the field. And if the color of the crop from our naked eyes changes from green to brown when it shouldn't be, then there could be a problem. Then we can see that there is a problem. So we need to ensure, we need to go to the field and see like what's happening in that region. It could be disease, maybe nutrient deficiency, pest infestation, probably environmental factors as well, on which we don't have much control, but certainly we have control on management factors. So we can look on that and try to correct it. So to give you an examples, what I have done is that I processed these satellite images of entire crop growing season of wheat for 2016-17 from December to April, December 2015 to 16. And let's see how we have used this data. So as simple as that, we can use for crop monitoring, we can use vegetative indices, which is a measure of the chlorophyll or greenness. I've used Ndvi, and there are several other indices, and it can give you the distribution of how well the crops are growing throughout the season. So I've created this animation. So it starts from December 24th, where we don't have, cover. The crop has just been planted or it's just started growing, so it wouldn't look green. And then as we move into the season, from December to January, green, February, green is growing, and then from March onwards, the wheat crop dries and gets ready to be harvested in late April or early May. So it's a progression that you can see how the crops are growing and drying, reaching maximum cover, and then drying off. So what information can we get? This is a processed satellite data. How we can get information? So I have selected of Allahabad district, whose area was greater than 1 hectare. A decision where when you are selecting a data, for example, satellite data, so you need to make sure that what information you need and at what scale or at what level you need. Because if your fields are smaller than the resolution of the satellite image, you wouldn't be able to see it. So that's why I have selected 1 hectare fields because Landsat constellation of satellites whose maximum spatial resolution is 30 meters multispectral, and it gets coarser as we go to thermal. So 30-meter resolution, we calculated that we would get at least 10 pixels if we have 1 hectare field. So that's how we selected, and then from those fields, we overlaid those fields, we digitized the boundaries of those fields in GIS environment, and then we overlaid those polygons on the Ndvi images, and we extracted the data. And let's see the data. How does it looks like on each specific image date? So this is how the data looks like. Essentially, it's a two-dimensional graph where we have Ndvi on y-axis and dates, image dates on x-axis. But then I have put another axis just to explain the variability. Like the dots, the blue dots that you would see, it's median values of Ndvi on those image dates. So obviously, median means that the value, half of the fields are more than that median value and half of the fields are less than the median value. And as we can see in December, it looks okay. We don't see much variability where the crop has just started growing. And then it continues to grow and reaches probably almost 90% full cover in January. But here, non-uniformity. If you see these spikes and then it drops and then again these spikes. So this is all non-uniformity because this is individual field data, average NDVI value of those individual fields. And that's where the problem lies. And then it continues to magnify, and we can see that in February, this is more non-uniformity, the spikes and the trough, it's more. And then once the crop gets drying, it again becomes normal distribution curve and it dries off. So what we see here is that at the peak cover or the full cover, there's a lot of non-uniformity. Some fields have reached the maximum or the potential of greenness, and some fields they're not able to reach that potential mark. This thing will have an impact ultimately on the yield. So if we can figure it out when they should be at full cover, what's going on, then maybe we can minimize or mitigate these low potential production issues. So as it's visible that we need to do something about these non-uniform fields in time. So next agricultural management aspect is the irrigation management. What and how we can do with remote sensing and GIS in irrigation management. So the first fundamental or the straightforward fact is that unregulated irrigation affects the yield. Unregulated means over or under, both. Then proper and accurate irrigation scheduling is required for better production. So irrigation scheduling have three components: when, how much to irrigate, and how to irrigate. So how to irrigate is more of a designing part, and I'll leave it for today's presentation. I will focus on when to irrigate and how much to irrigate, these two. How if we can know from remote sensing what we would like to know. So if we, for example, if we want to tell someone that, okay, how thirsty you are, so we need to know when he's thirsty and how much water he would require. So water loss is the key word that we are looking for. How thirsty the plant is, how thirsty the crop is. So that's what we are estimating through remote sensing, the water loss, evaporation and transpiration combined. It can be estimated via remote sensing techniques using surface energy balance approach. It's a very old approach, almost 20-25 years ago it was established, or maybe 30 years ago. People have been doing a lot of work in it. So I used one of those models, surface energy balance model, to process these images and estimate the water loss. And let's see a cumulative ET map, evapotranspiration map, or water loss map from the crop for the entire season. So this water loss is basically the amount of water that crops are using for their growth. So it should be at least at their potential if we want to have a good healthy crop. And let's see what we can extract the data, how we see these maps. So these maps are good for visual inspection, but we need to see some data. And again, if you see this graph, it has similar, it resembles with the non-uniformity that we were seeing in Ndvi. So here we can see that they are directly related, you know, how the crop is growing and how much water it is using. So water is a limiting factor. So it's, you know, either way, if the crop is not able to use water properly, there are some issues. And if it's not being resolved, then it's affecting its growth. And if we take the tehsil-wise distribution or the block-wise that I was talking about, that the administrative subdivisions of the Allahabad district, so it has 8 subdivisions, and we can see that there is a lot of variability. There is a subdivision called Korao, the first subdivision, how low water use is in the crop. And then we goes to Meja, where these last 3, Handia, Fulpur, and Meja divisions, subdivisions, how well they are using or how well the crops are being irrigated there. And we can see these error bars, and we can see that there is uh, less non-uniformity in these three as compared to the others. And this will reflect later on as well. We will see in the later slides. Now let's see some samples of within and among the field distribution. So within the field distribution, these two field individual fields, I have extracted the data. Field ID 64, which belongs to our major subdivision, which is showing in this graph. If you see on the left side, that's the last bar. So for us, this shows that in Meja, the water is being utilized by crops nicely. They are being nicely irrigated, and mostly they are uniform. So, and it's evident in one of the sample fields that I extracted the data for, and we can see that most of the irrigation is happening between 250 to 300 millimeters. And then as compared to another field, which is from Koran subdivision, we can see that there is a lot of non-uniformity, and the irrigation is ranging as low as from 50 millimeters and going high to maybe 200, 250, probably around that part. But there is a lot of non-uniformity. So this non-uniformity in the field are hurting their ultimate crop production. We need to focus on it. If we need to resolve it, if we need to get potential crop production, we need to sort this out. So what I did was that these water loss or water use values were estimated by running an energy balance model, and I tried to do a little comparison of from the previous studies from standard values. So let's see how this comparison looks like. So we interviewed the farmers, and according to them, they told us on an average that how much of an inch of water they put in the field and how many times throughout the season they do it. So we made a calculation, and from our calculation, it is 254 millimeter total. This much amount of average water that they have put in their wheat fields during a crop growing season. In the present study, what we estimated or we predicted was 261. So it is below 5% what we have estimated. And then if we compare it with the other sources, there was a similar study done in Indus Basin. Same model was used, and they predicted for wheat 360 millimeters for the entire season. And now to FAO 33, which recommends that for potential yield, at least 550 millimeter of water should be applied. I mean, or should be used or should be given to the crops for the use. So we can see that already we are quite below from the potential water that needs to be given to compensate for ET. And at the same time, we can see that there was a fair enough comparison. There are those two values, the farmer inputs and then the value that we estimated was pretty close. So we were in the ballpark region, and we can say that we can review our irrigation scheme or regime by using this data. Let's move on to the next aspect of crop management, which is yield prediction. Now, why do we like to predict yield? Obviously, to decide so many policies. Obviously, to see, I mean, it's not necessary that only policies needs to be decided, but we can predict the yield of a standing crop, and we can do some improvements as well, or some changes, or even changes for the next year. So it will be good to have a yield prediction, predicted value. And we use, again, a well-defined model, which uses biomass, harvest index, light use efficiencies, and photosynthetically active radiation. So these are all established model. I'm not going into the details of this model, otherwise it will take another, series of lectures. So let's see what we did, what we came out with. The greener areas are obviously more yield, and the red areas are no yield, or they don't have any crops. So we again use those same field boundaries that we had digitized, the 100 field, and then let's see. First of all, the average yield data of our subdivisions in Allahabad district. And again, we see the similar pattern as we were seeing in ET, that the highest average yield that we are getting is in these three sub-blocks, Phulpur, Handia, and Meja, as compared to Koran or Karchana, Surao, Allahabad. Allahabad is, urbanized area as well, so it's obvious that we are seeing so much of non-uniformity. But rest of the sub-blocks, subdivisions are agricultural based, so they shouldn't be having this much of non-uniformity. They should be producing nice as the last four subdivisions, Bara, Phulpur, Handia, and Meja are producing, or at least Phulpur, Handia, and Meja. This should be the average. So anyhow, let's see the individual samples of the field. So Meja, where we saw less non-uniformity, or it was see that individual field data, it gives you an idea that most of the yield was between the bracket of 3 to 3.5 ton per hectare. And this is evident that it doesn't have much non-uniformity. But at the same time, if we see a sample field from Koran subdivision, the yield is all over the place, starting from 0.5 to up to 3 ton per hectare, but it's very low overall, and lots of non-uniformity and lots of variation. So we don't would like to prefer to see this, because we need a uniform yield, we need a potential yield. And if we can learn lessons, we can go and do something better. Let's see some of the comparisons that I was able to do. So these average district level data, this is again available on the website of government website. This is the yield data. It varies between 2.2 to 2.4 ton per hectare for wheat in Allahabad. And the present study predicted 2.6. So again, we are pretty close to the average yield that farmers provided us, 2.7 ton per hectares for those 100 fields. We did a study and we asked farmers, and we were able to do an average yield of 2.7. And then the country average is 2.8. So somewhere we are lacking. We are even below the country average, despite of being one of the larger producer of wheat. And then obviously, the FAO recommendation is the potential yield should be up to 4 ton per hectare. So again, we are not reaching absolutely to the potential, which is be a cause of concern. Now let's mix it and see a term or terminology called water use efficiency. Our PM, Honorable PM, has also said that there should be more crop per drop. So this is where it comes from. Water use efficiency, crop yield per unit volume of water applied. So what it is? Yield is related to ET, or the water used by the crop. How it is related? Can you see these two maps of ET and yield that we have developed in this study? It provides a similar pattern. You can see a similar trend. There is similarity. There are striking similarities between the trend of these two maps. So maps are good for visual interpretation, but let's see on the graph, how does it looks like? So on the left side, we have the water used by the crops, and the right side we have average yield. So it's quite visible that all the subdivisions, these are average value for the subdivisions of Allahabad district. There is again a similar pattern where the ET is high, where the water use is high by the crop, the yield is also high as seen in Meja and Handia and Phulpur Bara subdivisions, and where the water use is low, in most of the cases, the yield is also low. Now, I mean, we have to be careful, obviously, that, there is a certain upper limit. We cannot keep on irrigating and hoping that it will increase our yield. There will be, a final log. I mean, obviously, if we go beyond that, what we are doing is we are waterlogging the field. So we need to be ensure of we don't do waterlogging. So when we do our regression and we see that how in these 8 subdivisions of Allahabad district between yield and ET, the average yield and total ET of the season, we can see a high correlation between these two, which again tells us that simply yield is related to ET or water used by crops to a certain limit. So to conclude, obviously this all data that we are talking about, satellite images or coming from drone, this is spatial data. So we are looking in space, we are looking at huge area, multiple fields at a time. So this is a huge leap in information. We can do a near real-time monitoring. We can make future predictions. We can even do a retrospective analysis, means we can go back into the history, because the satellites are coming and they are recording images for years. So we can go back to 10 years ago and we can get that image and process it and see how the irrigation regime or yield was 10 years, 20 years ago, as far as we can go. So geospatial technologies provide an excellent mean for managing agriculture. Things like we can monitor crops health, we can optimize the inputs like irrigation, fertilizers, we can do yield predictions, and we can evaluate the irrigation regime through water use efficiency. Then obviously the important aspect is better planning and informed decisions for farmers and farm manager, for policymakers in deciding the market price, and it can assist us in other logistic planning like storage, transportation, etc. Lastly, but not the least and very important, geospatial techniques should not claim to replace ground measurements. Rather, it complements or supplements. We cannot say that we have validated remote sensing and GIS techniques, or we have validated remote sensing. Because what we are getting in a satellite image is thousands, hundreds, millions of pixels, small divisions. There is no way until and unless we have a good ground-based data which are representing conditions in real conditions in the field, actually, which are representative of where the field can have a high yield. There are areas which will have higher yields, there will be areas which have lower yields, there will be areas where crops is generating more ET, lower ET. We need to have measurements at all those areas. Then only we can do a proper validation of remote sensing. But we need ground-based measurements. Where remote sensing help is, because obviously we cannot put stations at every nook and corner. So once we are confident enough with the on the basis of ground data, then we can validate our remote sensing. Otherwise, we can only say that it's a comparison at selected location. So anyhow, I mean, we have options, we have technology. It all depends how we can use it. So thank you very much for that. And I'm open for questions.
Okay, Dr. Shakti. Mic goes. right for the questions.
Thank you, sir. I have few questions in this session. Mr. Muhtar, he asked that can Landsat be utilized for calculating thickness or maybe the overall productivity of a crop? Landsat can be utilized or not?
Lancet for yield calculation, yield prediction.
Yield prediction.
Yes, it can be used, but you need to be uh, uh, you need to understand that whether the fields or whether the area that you are using for it, the resolution of those fields are within the resolution of Landsat image. Because if the fields are smaller than the resolution, then you won't be able to see the fields, and what you will be seeing is the mixed signatures of a large area. So it won't be accurate, or you may go wrong as well in that. So you have to be, yes, you can do it with Landsat, but you need to make sure about the resolution of the fields.
Okay. Thank you, sir. There's one more question from Rohit Lal, sir. He asked that in case of mixed cropping, how ET and yield estimation can be made and up to what accuracy?
In terms of mixed cropping,
how ET and yield estimation can be made?
Well, it's a very excellent question. Again, what boils down to is how much ground information we have. If it's a mixed cropping, is the resolution of our data well enough to differentiate between those mixed cropping? Is our data is able to differentiate between field to field, which are having different crops? It can be done, but again, the resolution is very important. And here, there are high resolution satellites like Sentinel, which is giving data at 10 meters, but then we might as well use drones, which have sub-meter accuracy, sub-meter resolution. So it's doable, but resolution.
From Ashutosh Ranjan, he asked that what preventive measures we should take or what management techniques we can adopt in order to match the FAO standard. In one slide, you have mentioned that we lack the FAO standard by some percentage. So he asked that what preventive measures can we take, or maybe a management techniques can we adopt to find a standard FAO standard.
Sure. See, what FAO does is that again, it's a very good question, and I would appreciate this question. What FAO does is they're talking about pristine condition or standard, highly standard condition. Just like when a car is manufactured, they will give you an average of 20 kilometers per liter, but it never happens. It never happens. It's like 10 or 15. So what we can do is that 20 is the maximum under all standard condition, everything well. But in actual condition, not everything goes well. There are certain things. But to reach to that potential, we need to make sure, first of all, is irrigation. Irrigation is one of the most important aspects. We need to supply enough water to fulfill the demand of the crop at the right time. Timing and amount is very important, at the right time, because again, there is a relation that even if you're providing good enough water, but the timing is not right, like flowering, then there will be a problem. Again, there will be a problem. So it will be really helpful to understand the potential ET and the right timing of the irrigation, those two factors.
Thank you, sir. It is a great day for me because being head, you generally ask questions from us, and today I'm asking.
I'm on the spot.
Thank you, sir. Thank you, sir.
Please ask me easy questions. I get nervous.
Thank you, sir. Thank you, sir. This is it from my
Thank
side.
you, Shakti.
Okay.
And thank you, Dr. Lal. We know more about ET, potential evapotranspiration, yield monitoring, yield modeling. And I hope the participants who are watching, they can see what things we are doing in our center and what they can do in future when they may think about higher studies from SHUATS in the Center for Geospatial Technologies. So now I would like to call our co-convener, Engineer CJ Wesley, who is also Joint Registrar Administration, to discuss about the university perspectives on this webinar. Engineer Wesley.
Thank you, Dr. Mishra. We have missed one of our speaker because of yesterday's storm. He is unable to join us today. Well, respected speakers of this international webinar, my dear participants, it is indeed a wonderful experience for all of us to listen to our learned speakers and experts in this international webinar. I hope all participants would have thoroughly educated through this platform that is provided by the Center of Geospatial Technologies of SHUATS. I take this opportunity to express on behalf of the university our sincere thanks to the speakers, the panelists, and each and every one of the participants who have registered for this international webinar and have witnessed the proceedings of yesterday and today. We had more than 1,700 participants registered in the webinar, which has been broadcasted through the Zoom platform, licensed Zoom platform. And simultaneously, we have been live streaming on our Facebook handle of the university. So if any of you have missed any of the lectures, both yesterday and today, you can readily watch the videos which are available on our university's Facebook handle, that is SHUATS_Allahabad. And also the videos will be available in our YouTube channel, that is Connect SHUATS. Dear participants, I hope after being thoroughly educated through this international webinar, all of you are eagerly waiting for the certificate, participation certificate, and it is indeed ready. And you can download your certificates from our university website, that is www.shuats.edu.in/RGIS certificate. Through this link, you'll be able to download your respective certificates, participation certificates, using the credentials like your email ID and the mobile number which you have used to register for this webinar. I'll just show the link for you all to note down.
Shakti, you can also type the link once it's on the screen in the chat box.
Yeah, the link is, you can note down www.shuats.edu.in/RGIS certificate. I certainly hope you will have a wonderful experience in downloading the certificates using the credentials like your email ID and mobile number. And I request Dr. Shakti to drop down the link in the chat box to all so that it can readily be visible to everyone. And I congratulate especially the Department of Geospatial Technologies for conducting such an international webinar of this stature, to have speakers from all over the world, from USA, Europe, and from Asian countries. I congratulate the center head, Dr. Deepak Lal, for organizing, for planning such a wonderful webinar. And this is series 1, I presume. We are about to have series 2, series 3, and many more in different topics, different streams where remote sensing and GIS will be applicable. So stay tuned for more webinars, for more series to come. And also, many webinars are being organized by the university department. You can get the details from our Facebook page as well as from the website, our university website. The admissions for the session 2020-21 is open. You can register for any of the undergraduate programs, postgraduate programs. We do offer 44 undergraduate programs and 104 postgraduate programs. Many programs are under open online counseling, and some programs in agriculture and allied fields are under entrance exam, which will be held on 2nd of August. So I request you all to kindly visit our website shuats.edu.in, www.shuats.edu.in. These words, I wish you all wonderful days ahead. Stay safe. With together, if we work hard, if we stay safe, we will contribute to the overall cause to overcome this pandemic. Thank you. And over to you, Dr. Mishra.
Thank you, Engineer Wesley, for such a nice information about admissions, about the certificates, and for next coming series of seminars. Now I would like to request again Dr. Shakti Suryavanshi to give the findings and conclusion of today's webinar that titles Geospatial Technologies for Managing Agriculture, application from USA, Europe, and Asia. So he will conclude what are the findings, what we have learned from this webinar, and what are the future aspects where we are looking. So over to again Dr. Shakti Suryavanshi.
Thank you, Dr. Ashish. On the day one, Mr. Vishnu Chandra started the session with the topic Geospatial Technologies in Agriculture, a multi-layer GIS framework as National ICT Vision. So in that topic, he covered the various application functionalities of NIC. He also discussed the various research platforms and services for the governance like Bharat Maps, Gram Manchitra, E-Way-Bill, Geospatial-based decision support system for panchayats, public finance management system, and discussed how these state-of-the-art technologies will trickle down and benefit to the lowest section of the society. The next speaker, yesterday's speaker, was Dr. Daniel Zacharias from US Davis, USA. Dr. Zakaria provided an overview on applied research efforts for improvement in agriculture water management in California. He discussed the background information on agriculture in California and provided an insight into the long-term trends and water-related challenges. He focused his lecture on the research and extension effort to improve agriculture water management. He focused on examples of integration between geospatial and ground-based technologies. Also share his experiences on water use in micro-irrigated pistachio orchard and to how to improve water resource planning and irrigation scheduling. On yesterday, our next guest speaker was Dr. S.P. Agrawal from IIRS Dehradun. He discussed the various remote sensing and GIS applications for water resource management. He enlightened with various Indian Earth observation missions and focused on various applications of remote sensing in predicting precipitation, evapotranspiration, monitoring and mapping of various water bodies like ponds, reservoirs, lakes, and also impart his knowledge of flood mapping. He also provides some insight into the hydrological modeling and its various applications in water source management. Our last guest speaker of previous day was Mr. M.K. Hazarika sir from AIT Bangkok. He discussed his topic in various applications of geoinformatics in agriculture. He discussed about various satellite data in crop monitoring and yield forecasting, where he highlights the use of drones in crop monitoring. He enlightened the participants with the advances in big data in agriculture. He also discussed some models for agroecology zonation using state-of-the-art technology. For today's lecture, Dr. Guan started today's lecture with the topic remote sensing techniques as a tool for agriculture water management. He discussed the method to calculate crop water requirement using remote sensing techniques and highlighted the use of different models utilized in agriculture. Dr. Tapan followed it in the next session and focused on climate change and California's irrigated agriculture. He discussed historic as well as future climate trends in California. He also illustrated the agriculture impact in terms of declining yield, crop growing season shifts, and pest and disease pressure. He also highlighted the importance of machine learning and decision support system for agroclimate. Our last guest speaker was our head of department and Professor Deepak Lal. He, during his presentation, highlighted the prospects of geospatial techniques for sustainable and profitable agriculture. He discussed the existing challenges in farm monitoring and tried to find solution for that. He also focused on geospatial technologies that can help in agriculture health monitoring, irrigation management, yield prediction, and water use efficiency. Hope this will help you, these 2 days will help you for adapting your knowledge towards geospatial technologies. Thank you, and over to Dr. Atish, sir.
Thank you, Dr. Shakti Survanshi. So now I would like to invite our webinar organizing secretary, Dr. Mukesh Kumar, for the vote of thanks. Okay, Dr. Mukesh Kumar.
Thank you, Dr. Mishra. Honorable professors, scientists, and dear participants, good afternoon to you all. I deem it a great honor to propose the vote of thanks to all who have helped us in making this webinar series such a resounding success. I would like to express our profound gratitude to our Honorable Vice Chancellor, SHUATS, Prayagraj. We are thankful to you, sir, for giving us this opportunity to conduct this webinar series 1. I also like to thank our Pro-Vice Chancellors, Registrar, and Deans for their moral support. Now, most importantly, I would like to thank our distinguished speakers, Dr. Tapan B. Pathak, a specialist in climate adaptation in agriculture from University of California, Merced, USA. Thank you, sir. Second speaker was Juan Miguel Ramirez Cuesta, remote sensing and GIS specialist from Spanish National Research Council, Murcia, Spain. And then our head from the center, Dr. Deepak Lal, professor and head, Center for Geospatial Technologies. Also, thank you, Professor Dr. Sir Deepak Sir, head, Center for Geospatial Technologies, for your moral support and guidance. A special thanks to Joint Registrar Engineer C.J. Wesley for supporting all the technical issue in very professional way. Thank you, sir, for your kind support. I am happy to express vote of thanks to our staff member, Dr. A.R. Mishra, sir, and Dr. Shakti Survanshi, who have made this webinar a great success. Finally, a wonderful student who have turned up in such a great number during the COVID-19 pandemic, not only from the department and university, but also from the other department and institute throughout the world. Thank you so much for your kind cooperation. Once again, I thank all for your cordial coordination. Thank you very much, sir.
Thank you, Dr. Mukesh. It was nice to have such a wonderful webinar. Now I would like to request again our chaplain, Brother Lalchung, to lead us in a closing prayer. Brother Lalchung.
Let us look to the Lord in prayer. Heavenly Father, we thank you for answering our prayers and guiding us from the beginning of the webinar till the end of time, Lord. We thank you. And we thank you for the leadership of our Vice Chancellor, Lord, for enabling this webinar to be held also. We also remember the founder, Lord, Sam Higginbottom, who has so much heart for the people of India and for the farmers who are struggling with the local equipments and wanting to develop with the scientific tools. And Lord, with the dreams and aspirations, trying to help the needy, serving the land, and feed the hungry, bringing up this motto, Lord, he has started this university as an institution. And now we have come to this level of an university. It's all because of your grace and your leading hands. We thank you very much, Lord, for the lives of the founder and for what you have inculcated. And today, Lord, we are able to come here and, Lord, be learning and getting from each other, Lord, information. So we thank you for the speakers, the scientists, and Lord, for the students who also are sitting together and at this very time of struggles that we are going through, Lord. We thank you for enabling us to have this kind of webinar. And I pray that, Lord, all that was discussed by the scientists and, Lord, all that we have heard may be used for the development and advancement of our country and for the development and advancement of humanity, particularly, Lord. So that, Lord, this will be for the constructive use of human gain, and Lord, so that we all would live together in peace and harmony. And I pray that, Lord, you will bless us. And thank you very much for the life of the head of the department, Deepak Lal sir, and thank you very much for his leadership and for the way he has led this department also. May you bless him and may you guide him as well. We thank you for all the people who participated in bringing us to the end of this session. With thanksgiving, we pray in Jesus' name. Amen.
Thank you, Brother Lalju. We highly appreciate your effort and for participation. So now it was great hearing our accomplished speaker, and thank you everyone. It's been a pleasure being with you in a 2 days webinar session. On behalf of Center for Geospatial Technologies, as a webinar convener, I would like to express my gratitude to all of you who come together on this online platform from across the globe to share your knowledge with us. Your feedback and suggestions are most welcome. You will receive an email within 24 hours from now. It is requested that please fill your suggestions as well as feedback, and it will go to your email, and then it will revert to us. So according to your feedback and suggestions, we can plan for the future webinars. Though participants can download their certificate from now from the website as discussed by Engineer Wesley. It was just the beginning of our webinar series, and we'll keep running webinar on relevant areas in the field of remote sensing and GIS. To know more about our program, that is MTech, MSc, Diploma in Remote Sensing and GIS, PhD program in Remote Sensing and GIS, you may contact in our website to our dean, VIAET, or us also on social media like Facebook, Instagram, or WhatsApp. We are available, so you feel free to contact us anytime. And thank you very much. Thank you to all, especially our head of Geospatial Technologies and our technical support, Engineer CJ Wesley, and all of you. Thank you very much.
I would also like to propose an informal.
For Geospatial Technologies. The Center for Geospatial Technologies, SHUATS, logging off now. Jai Ishu,
Wesley,
Jai Hind, and Jai Bharat.